It's a pleasure to have Tisha with us, Tisha Vishwas. So she's finishing her PhD at the University of Calcutta. So she is doing her PhD with Morning the London. So she'll be talking about various aspects of beyond the standard model physics via EFT approach. So over to you.
So I will be mainly talking about the search for new physics via this effective field theory approach. And within it, I will mainly focus on the SMEFT, the standard model effective field theory. And towards the end, I will share one work on action-like particle effective field theory. So the works are based on these papers, and my collaborators are Dr. Ananda and Dr. Vishwas. So firstly, I'll begin with what is SMEFT and why is it becoming so prevalent now. So the standard model, with all its brilliance, has, as we know, that it has explained most of the observations remarkably well, be it the low energy observables or to the multi-particle production at the LHC. So still no new physics beyond the standard model has been observed yet, no evident signal. So we believe that since the standard model has still left some questions unanswered, like the neutrino mass problem, the baryon asymmetry, to name a few. So we all believe that there is some theory more fundamental than the standard model, and generically we search for these new physics. We either directly through some new resonant production, or indirectly by measuring precisely the standard model interactions. So I will mainly focus on the searches for beyond the standard model signals at the LHC, and as I said that so far no new physics, no direct hint for new physics has been observed at the LHC. So it might be the case that new physics is standing just beyond the reach of the LHC, and when integrated out, this would lead to some indirect effects in the couplings of the standard model particles. So we need to look for some new non-resonant physics effects at the LHC, non-resonant physics effects. So the effective field theory, it's a field theory that describes the low energy phenomena of a UV sector in terms of the light degrees of freedom. So whenever we talk of these effective field theories, we need three ingredients. What are the degree? We need the degrees of freedom. We need to know about the degrees of freedom. They need to be light. And what are the symmetries of the theory, and an expansion parameter to describe my effective field theory. So within this EFT, I will be talking about this standard model effective field theory, wherein I will consider my light degrees of freedom as the standard model fields and the symmetries of the standard model. But this theory allows for dimension D greater than 4 operators. The fundamental assumption in this theory is that the new physics is way above the scale. New physics is at a scale which is much higher than the electroweak scale, or the energy, or the scale of the energy of the experiment that I'm carrying out. So this effective field theory expansion in terms of this Lagrangian can be expanded in this series, where standard model is the lowest order term in this expansion, and we have these higher dimensional operators Qk, which are composed of the standard model fields, and they are suppressed by this cutoff scale called lambda, and their couplings, the associated couplings with these higher dimensional operators are these CKs that contain within them the BSM effects. So our BSM goal is to determine these Wilson coefficients associated with these higher dimensional operators. So
what about log lambda type terms?
Log lambda type.
Yeah, for example, log lambda over lambda squared. Okay, that will also vanish when you take lambda to infinity limit. So the effective field theory can in principle, in fact, in the chiral effective Lagrangian.
Yes. Yes.
So why do you leave them out here?
Firstly, in the chiral perturbation theory, we need to integrate out some degrees of freedom. I am talking here of all these standard of these operators. Effectively, this Lagrangian can be described for the chiral Lagrangian as well, where we can have log terms also. And for the large log terms that you are saying, we can perform resummation of log terms and but effectively, even those terms can be expanded in this series where we have this 1 over lambda power expansion and the higher dimensional operators.
My second question is, what if your new physics violates the symmetries of the standard model? Then even when you integrate it out, it will induce terms. Higher dimension maybe, but not having the symmetries of the standard model.
Yes, that is possible.
But that's also you have ignored.
Yeah, I'm saying that I'm focusing on one particular type of effective field theory, which is this standard model effective field theory, where all the field contents are my standard model particles only. And if you are saying that there is some theory that has some other symmetries other than the standard model, so we can have such theories, and suppose it has some. I mean, we can even if it has some extra symmetry which is not there in the standard model, I can firstly write an effective theory for that. What I need to ensure is that whatever the high new physics state is at high scale, when I'm seeing when I'm studying a particular observable at a particular energy scale, whether there is a large difference between the scale that I'm probing and the scale.
Take for example, Fermi theory is an effective theory.
Yes.
Standard model then parity violation. So it will induce even in the Fermi theory parity violating terms, which are very important.
Yes.
Okay. So by not including such terms, these are still higher order and they're only involve light fields, but they're essential.
So this is a subset of effective field theories. There are many other effective field theories where these are taken into account. So in this simple standard model effective field theory, like she's talking about, as far as the logarithm term goes, even in standard model effective field theory, we can have those.
We want the theory to be effective.
Yes.
So there is no such thing as a simple effective field.
Yes.
So you write all possible terms.
Yeah.
Okay.
Yeah.
And keeping some symmetries. But if the higher theory violates those symmetries, you can't do that. So I'm only wondering whether, first of all, log lambda is more subtle than.
Okay, the logs can actually arise. So it's a non-analytic term, so it can arise in various ways. One, if we do loop computation, so this is basically when she writes out the leading order term, the logs don't arise. And also from RGEs, you can induce logarithm terms. So those also come in effective field theories when you are going from one scale to another. Also, it's possible to sometimes redefine somewhat non-analytic looking terms into analytic looking terms by field redefinitions, where this would actually look like what she has here.
I'm not sure about that, but it's true the renormalization group can.
Yeah, like from the anomalous dimension matrix, you will get.
Suppose we have a log lambda over m term, where there is a large difference between lambda and m. So this log term will be very large. So suppose I rewrite this log lambda over m as suppose log lambda over mu plus log mu over n, and then I will run that mu that mu scale from high end. I will do the running here. So that's where the RG will come. I mean, I need to run from one high scale to one low scale.
Is it equivalent to say that that the CK can include log lambda pieces? That one way of implementing this.
if we have loops, suppose an interaction where an interaction at one loop order, suppose. So there we can have such log.
So I can think of that as hidden in CK. If there are log lambda, I can push it into CK, right?
Yes.
And that is one way to answer the question.
In fact, each term, every order in lambda, C times Q is RG invariant in some sense. C evolves with respect to mu r square, and an operator also evolves with respect to mu square. But C is known in perturbation theory to set an order. It's a Wilson coefficient. So you truncate your series to certain order. So you end up with a coefficient of lambda or lambda square with a non-zero log q square or log some I scale over renormalization scale mu r square. So it will be present in this expression if you truncate your Wilson coefficient.
So
Otherwise, it's in RG invariant in some sense. And each coefficient, because it's Lagrangian, it has to be RG invariant. So C times Q at every order is RG invariant.
So one should distinguish the mu and lambda. By lambda here is meant some high scale physical scale.
Yes.
And the language you are using is mu.
Given lambda, still there is a mu dependency.
Yeah.
Which is actually, it's nothing to do with the cutoff and what.
Although related, they are talking about slightly different things. Like that. This is actually some high scale lambda, which is the fixed scale.
But the coefficients can have lambda, log lambda over this mu r square.
That I would think of as pushing into the CK. I mean, this is matched at tree level, right? I mean, this is a tree level.
That's what we say. CK has log lambda coefficient. So it's a Wilson coefficient with the calculable, which is a function of the scale.
But that is log mu. That's a renormalization.
But it loves some other scale that's log lambda by.
Yeah. So I'm not sure about that because it is an expansion in lambda, which is thought of as some.
But there'll be logarithmic corrections. No?
Yeah. So you can have log mu
It's
or
computable in your quantum field theory. That is the first correction that you get logs.
log mu.
Then you get a log 1 by lambda. So the C's should contain the degree.
Right. So sorry about the symmetry thing. You mean the standard model gauge symmetry?
Right.
But perhaps this question is about the global symmetries and all that, which are assumed to be general enough that we can include such L violation, B violation terms in your.
Yes.
Yeah, those will be present, be validating.
So what you mean there is really the standard model gauge symmetry, but not necessarily the global.
Yeah. So why is this EFTs are so prevalent now? So EFTs have been in use in particle physics since a long time. For example, in this interpretation of the low energy precise measurements, G-2 measurements, flavor observables, SNT parameters, and so on. That could probe new physics scales up to order few TeV. So nowadays at the LHC, what is new at the Y at the LHC, we are so much concerned with the CFTs because we have the access to the full set of standard model dynamical fields and a large range of kinematical situations. So we need to test the properties of these standard model particles in a range of kinematical range of energies and angles as well, which is new and untested than before. So SMEFT, it's a systematical theoretical framework that can be used to study the standard model particle interactions that allows for the VSM effects, as we see that the higher dimensional operators, which are invariant under the standard model gauge group.
Why should it be invariant in the standard model gauge group? Because there the gauge is spontaneously broken.
Yes, even after breaking.
So why do you put this restriction?
Yes, we can have a different kind of EFT there as well. But what I'm saying is, they will be within a subgroup of SMEFT. After symmetry breaking, the effective field theory that I'm having, suppose a weak effective theory, that is a subset of SMEFT.
So sorry, one answer could be that phenomenologically, this is a good way of proceeding because if the new physics breaks the standard model gauge symmetries, it will really change a lot of the observables, which we have not observed. So it seems like from low energy point of view, standard model gauge symmetries are exact. And it has to be spontaneously broken like in the standard. If you have other kinds of breaking in the new physics sector itself, it would imply effects which we have not seen. So it's a phenomenological answer, which is why most people proceed that way. But if you break a new physics breaks it, then it can break. But as you say, you're not considering that kind. For good phenomenological reasons.
So if we observe something around the electric scale, then we include it, and then we define our EFT. It won't be a standard model EFT anymore.
Yeah, so,
It will be some non-standard model.
we have not observed any such
That
breaking
is
of gauge symmetries.
Yes.
Everything seems to be consistent with
the standard model.
the spontaneous breaking like in the standard. So it's an assumption, as you point out, that the new physics also respects the standard model gauge symmetry.
That assumption is like experiment.
It's an assumption.
Experiment dependent assumption.
It's phenomenal.
Yeah, phenomenology, motivated by low energy.
And in fact, if you find data which breaks it, you'll be very happy.
That's right. Then we won't be doing EFTs any longer.
Yes, the main assumption is that whatever new physics is there, that is perturbative. The standard model is the leading order effect, and whatever new physics is contained in these higher dimensional operators, they are perturbative. So at the and within it, within this SMEFT Lagrangian, as we see that at dimension 5 we have only one operator, that is lepton number violating, that gives Majorana mass to the neutrinos. And
But is it the only effect of the dimension 5 operator
yes,
to give Majorana mass, or is there any other effect of that?
Yeah.
Now, the reason why I'm asking is, without checking the effective theory at dimension 5, why should one go to dimension 6?
yes, I will come to it. So at the dimension 6, we have 59 total operators, and those 59 operators are the ones that give leading order deviation to the interactions of the standard model particles. So if we see any deviation in the coupling of, suppose, Higgs vector boson interaction, Higgs gauge interaction, which HBB buttons. So that deviation is contained by the operator which is at dimension 6 only, not at dimension 5. So that is why dimension 6 operators are the ones that give leading order deviation to the standard model interactions. And there are 59 such operators only. I will show those operators. There are 15 bosonic operators, 19 to both fermionic, one fermionic current operators.
So you have 59 parameters?
Within these 59 operators also, if we consider flavor structure, hyperconjugations of the operators, then if we consider all these effects
So how
together,
many parameters?
2,499, which is huge. 2,499.
So, I mean, with so many parameters, can you
That is
test
why
anything?
that is why it is challenging theoretically and experimentally both.
This is with CP conservation.
Yes.
We relax that already.
The CP validating ones are included in the 2499,
Yes.
No, but not in the 15.
not in the CP.
And some flavor structure also.
Yes.
Minimal flavor. And dimension 5, this.
Yeah. You can have some operators. I'm showing here some of the those dimension 6 operators. So here, if we have this kind of operator and we take the hyperconjugate of this operator, then it will lead to some other operator. If you take the conjugate of each field, like suppose we have psi bar, so psi dagger, gamma 0 dagger of that.
Yeah, why the hyper? What is hyper?
Conjugate, I understand. What is hyperconjugate?
Being conjugate of every field, is that what?
Yes.
Or writing every field as a conjugate. That's
Yes.
called hyperconjugate. not just adding remission conjugate term, but
Sorry, extremely sorry, it's Harnish.
oh, remission.
Sorry. Okay, sorry. So, these are some of the dimension 6 operators. So, within it, I will focus on only 4 of these operators, 4 classes of these operators. Now, I will very briefly describe these 4 classes of operators. So, I mean, these X cube, they represent the field strength, the fields, the bosonic fields interaction only. And this class of operator, it affects the Higgs potential only. And this class of operator, as you see, it is basically phi dagger phi, phi dagger times the U-cover interaction. And this set of operator, it induces modification in the gauge Higgs vertex. So we have phi dagger phi times the standard model interaction of G mu mu or B mu mu. These kind of operators, and these twiddle are the CP violating interactions. So, and these 2 set of operators, they contain one fermionic current. Here we have this vector current of fermions, and this set has tensor current of fermions. So, as I said, that I will be focusing on these 4 classes. So, notice that here where we have this tensorial current. Here it's a left-handed doublet. This L represents the left-handed doublet, and this E represents a right-handed singlet. And here we have either a left-handed current or a right-handed current, fermionic current. So I will be referring to these currents again and again. That's why I'm saying it here. So here you see that both the fermions, they have the same helicity. They are either left-handed or right-handed. But here in this case, we always have a chirolytic flipping interaction here. So here one is left-handed and one is right-handed. Okay. So moving on, I will refer to these operators in some of the processes that I will consider. So to answer first that how well we know, how much we can tell about the SMEFT, we first need to know how well we know the standard model. So these are some of the summary plots that we often see in the experimental collaboration by collaborations of ETLAS and CMS. So you see here, for example, this plot shows the cross section of various processes at the LHC. The more common these processes are towards as we go along this x-axis. Here we have a higher cross section for this PP collisions at the LHC. Towards here we have a lot of W production, Z production, and towards this left end we have the rarer processes, which is this multi-particle production with top particles. So the summary of these plots is that my theory, the theory matches extremely well with the experimental measurements. Whatever little uncertainty that we are seeing, they basically indicate that for the experimental observation that I am seeing is close to my standard model expectation. So whatever new physics is, it needs to be again, it needs to be perturbative. It needs to be a very small effect that is enclosed within those higher dimensional operators. So similarly, this plot also here for different, for example, this Higgs production, various production. I'm sure it is not visible. So for this Higgs production, and this Higgs is decaying to different channels. For example, Higgs to WW via VPF, Higgs to tau tau, but the net, the crux of the thing of these plots is that all my experimental data is matching extremely well with the standard model expectation. So,
before you go on,
yeah.
What about things like G-2?
Yes.
So, which of these extra terms?
Yes.
What level do that? Because that is precise.
Yes, that is extremely precise. So,
And also electric dipole moment.
Yes. So they can be G minus 2, as we know that these are the dipole operators that can effectively describe the G minus 2 effect. So their coefficients, they need to be small up to the to reach the precision of the G minus 2. So they are also enclosed by these dimension 6 operators. So we will basically describe the collider probes to search these new physics effects. So there are dedicated searches which define some signal regions which is optimized to describe to discriminate between the standard model and the SMEFT with this kind of amplitude square expansion. And we also need to reinterpret those existing measurements which are for the standard model measurements only, and we need to reuse those measurements and combine these measurements into a global analysis. And that's why, as I said, that there are 2,499 operators. So it's a game of matching hundreds of observables with a very large parameter space. And to do it consistently, considering all the EFT directions, it's a very difficult challenge even till now. So what we are doing is we are considering process by process how well we can distinguish between these EFT effects against the standard model interaction. So
your point of view is that there is some theory which corrects at a very high mass scale and you are integrating them out to get this.
yes. Yes.
That mass scale information should also be there.
Yes, that is within this. Like here, I'm saying that it is within this C over lambda square. I will describe how we can get information from these C over lambda square. These the coefficients of those higher dimensional operators, they carry within them the PSM.
But you could also take just higher dimensional operators, adding them to the standard model Lagrangian and consider that to be the fundamental thing.
Yes, yes.
That also you could do.
Yes, we are doing this only.
Now you are saying that there is a more fundamental theory which you are integrating out to get this. I think there is a deeper view.
Okay, so we need whatever theory, we need to match the theory with the experimental observations. The experiments that we are carrying out is at a low scale. Since we are not able to find any new physics hint, any evidence, so we conclude that the new physics is at a very high scale compared to the energy scale that we are carrying out.
If you take the entire Lagrangian to be the fundamental theory, then lambda would be that scale.
So there is one certainty here. So the way the standard model effective field theory is written, it's under the assumption that the terms that the physics is decoupled completely from standard model. So that's one of the reasons why we are.
What is the need for that?
So there is no need actually. So the standard model EFT is one simplified version of effective field theory. So there is another another popular effective field theory which is called the Higgs effective field theory or the HEFT. In the HEFT, the decoupling is not so apparent. So the new physics may not be fully decoupled from the standard model, and then you won't be able to write it in this way. And in the standard model effective field theory, the way it's written, all these Wilson coefficients are independent of each other, and through each operator, you are able to get multiple deformations. Say, for example, from an operator which comes with two scalar fields, two fermionic fields, you will be able to modify the mass term of the fermion. You will be able to modify the Yukawa term of the fermion with the Higgs. And you will be able to write also a two fermion, two scalar.
How is this picture different from the view that the entire Lagrangian is fundamental Lagrangian and the new couplings are at a different scale?
Yes.
Yeah, I think it's the same thing. You are doing RG on that.
Yeah, so RG is basically we are doing so because EFTs are in general non-renormalizable. We are renormalizing them order by order. Like we are
counter term renormalizable.
Yes.
Only a part is renormalizable, but the rest is not renormalizable.
So, but like we renormalize the dimension 6 parts separately. Then we go to the dimension 8. We renormalize them separately. So we renormalize order by order separately. So as I was saying,
I just don't understand the comment that it's coming from a more microscopic.
So
That I don't know.
the more micro,
Otherwise it is fine.
so the
I
more
don't
You
micro,
can forget that statement because no one
Yeah.
knows what that theory is.
yeah.
No, but I think that
What
there
actually
can be an
performs that
effect in the
integration?
I think there can be an effect in the inter.
So,
But anyway,
I'll just like in one sentence, and say, so it's basically a tool. So it's not a replacement for a theory. So the effective field theory's benefit is that we don't have to like immediately know what the bigger theory is. So if we know these directions right now, so we'll be able to probe these directions, and these could be mapped onto like multiple UV theories in future. So the experimentalists will only give us the constraints on these Wilson coefficients.
yeah,
And then
I just
we
don't
can-
see the.
No, but Shabha, that is what he's asking. There is no.
There is no need for assuming that there is a
So
unique
so don't assume it. I'm saying.
Yeah,
all
so that's the
facts
bottom up
are
approach. So that's the bottom up approach where we don't
The alternative time counter term normalization.
So that's how the bottom up approach where we
That's
don't
what I'm
assume
saying, yeah.
what new physics.
So if you don't like that, you can forget about it.
Yeah, forget it.
But I just wait until the interpretation is done. No,
Correct.
So as you approach the scale lambda, if you think of it physically, if you are allowed to do scattering close to the scale lambda, then you will break down, right? This
Yes.
theory will break down. So you need a UV completion at that stage.
Yeah, but now-
This lambda is just making the couplings dimensionality issue.
Yes.
Yeah.
So all that
approach-
you need
As
you just
moment you approach that lambda,
no,
there
nothing
will
is
be
getting down, nothing is going to, you might have to take another interaction.
no, perturbatively that theory will have a problem.
Correct.
No,
Unitarity will be violated.
no, you might have to include a higher interactions.
Yeah,
You can normalize it and
No,
within a certain scale.
because you need the arbitrary number of orders in lambda.
This is a lot
As
of
you approach
complex.
lambda.
Only if you do a finite energy experiment, only a finite number of couplings will be active. And you renormalize them
I'm
and get the
saying
theory.
you do
If you
experiments approaching the scale lambda.
Whatever the, yeah,
Then you need.
then you need higher couplings, that's all. It's not coming from a.
It is unrestricted. You need
It's
all
not
of
coming for, no, not all. Oh, no, not all. And
because lambda to the 25th will also contribute, lambda to the 200
He's
will also.
not playing it there, so let
So
us
all
not.
orders
is
will
scale,
go.
there will be
And it
scales.
will be useless as an effective.
No, let us not go there. Right now, you can just start with this, like, gradually.
I think that reasoning is behind the assumption. There is a UV conflict theory.
No,
which may not be.
It's just as an effective theory, it's useless. Okay, we can talk
Yeah,
about
okay,
it later.
we can talk about it.
So the first process that I will talk about is the vector boson fusion Gibbs production in the SMEFT. So these are the Feynman diagrams. In the first one represents this standard model Feynman diagram for Gibbs plus 2 jets. These are the diagrams that get induced when we have these higher dimensional operators included. So the first diagram that is induced by the modification of this Higgs gauge coupling comes from these bosonic operators, and there are a lot of studies already in the literature on these set of operators. So but I will mainly focus on this 4-point current interaction of two quarks, a Higgs and a gauge. This 4-point vertex, which is induced by these current operators as well as the dipole operators. And I will mainly focus on the kinematics of these jets. So the Higgs, whatever the Higgs is decaying to, I have considered here the Higgs decaying to 2 photons, but this analysis is applicable to all the, if we consider all the decay channels, as I have mainly utilized the jet kinematics. So the BF jet kinematics, as we know that we have 2 forward jets which have very large rapidity gap between them. And
So you're assuming that these higher operator corrections in loop diagrams are not important.
here I have considered 3-level interactions only. In the standard model, actually I have checked at 1 loop order in QCD. So there is a difference being like I have used the jet kinematics only. So within the kinematics of the jets, there is a difference if we consider standard model at 1 loop and SMEFT at 1 loop. So that but that difference is less compared to the tree level effect.
This
So
is the effect of running from lambda to the scale.
here
of,
I have, yes, here I have not assumed any specific value of lambda. I am,
When you say you check and it is a small effect, that
Yes.
will assume some scale for lambda, right?
yes, so the effect is contained within C over lambda square. So the constraint, so to comment something about the lambda scale, I need to assume some value for C as well. So that when I assume some value for C, that incorporates some model, UV model independence information. Some UV model dependent
Do it in a
information.
purely UV independent way
Yes,
by just saying that
exactly.
there is a certain lambda. And I take an effective theory defined there. And I'm going to run at one loop or whatever, one loop from that lambda down to the scale of this observable.
Yes,
And you can ask what is the size of that lambda.
yes.
As lambda becomes large, it will, the size of this contribution will grow, right? So when you say you have checked then and it is small, you perhaps mean that lambda is not very large, right? It's about TeV or 10
Yes,
TeV,
yes.
or not 10 to the 16 TeV. So some operators may grow quite a bit. You run it from a very high scale.
Just to give you an example, so we studied it like just at one loop when we include these operators in one loop. So when we include the RGs, so if you vary the scale, say from 1 TeV to 3 TeV, the constraints actually change. So we basically show it as a function of the lambda. So there'll be contours for different lambdas.
But changes only a little bit from one.
Changes a little bit, but
10%.
2%, right?
But if you run it all the way up to
If
10
you
to
run
the
it,
16 TeV, then perhaps some operators, it depends on the operator. Some operators can receive large effects, right?
Also, like there's more subtleties to these loop calculations because, like, when you do the RGs, the operators mix among themselves. Also, new operators are created which can give rise to new signatures which you were not looking at before. So these
But
set
if
of
your effective theory is general enough, those operators were already included to begin with.
so yeah, like if you're exactly, but like for example, say so that's not how
So
EFT
new
analysis
operators
is.
cannot be.
Yeah, I agree. So that's not how usually EFT analysis is done. So EFT analysis.
Yeah,
usually
these
is done
are
is
considered a subset.
you consider
Yeah,
some
and you can
observables
Yeah.
and then what operators contribute to these observables. You start with that, and then when you run this, you see that you are getting some operators
In some
which,
other observable.
which are
So
I have a question. So I want to ask what is the order of contribution of, let's say, your six dimensional operator, first first coming FMELT is comparable to your standard model order region, something like, let's say, second order, like my second order, NNRO result I get, and if it is, this result is comparable to your six-dimensional operator. Are you getting my question?
yes, it could be. So you
Because the question
it
is.
depends on the value of this C over lambda square. So if you if it is I mean NNLO if I consider it is less than the effect is less than 10%, say 5% effect I'm seeing the correction with higher order correction. So if the C over if including this NLO effect, my C over lambda square will accordingly you will put a constant on C over lambda.
No, so in the previous slide, you put like there is a difference between your standard model result and experimental result that you are going to say that okay, we will accommodate this into standard
With the
model.
higher dimensional operation.
So I think what Vaibhav is asking is when you take these extra dimensional operators, what is the percentage contribution of them with respect to the standard model result?
It's around 10%.
Then maybe you have to include NLO, NNLO,
Yes.
all higher order.
Maybe we don't
Standard model
have
contributions
yes.
before you can even consider the
So
dimension 6 operator model.
I think I think I mean Shankar can comment better, but I think whatever the precision of if we choose the precision of the standard model at NLO, The SMEFT should also match the precision of the standard model. The SMEFT should also be done at NLO order.
But wouldn't that question depends on the scale where they're,
Exactly.
that's a very logical scale.
Yeah, but she's applying it to colliders, right? So there's a scale, well-defined scale.
But we don't know when the new dimensions are appearing, that is a scale that we don't know. You can
Yeah, I
always
agree with that.
tune
So
it
it
to
is,
satisfy experiments.
yeah,
You can
it-
always tune it to satisfy.
Yeah, it all depends on lambda. If you
Yeah.
lower lambda significantly, which is what you're saying, right?
Yeah.
If you lower it a lot, then it can even exceed the.
Whatever
size of
whatever result you get experimentally, you can always choose a lambda.
In certain operators, you can tolerate a very low lambda, right? You
I
can
think
get
that
huge order one correction.
Take a process where the standard model contribution is very small. So that you can say that all your.
I think some independent discrepancies if you have, then you could see the entire framework is matching.
And
I was going to ask that question whether that is the scenario. I don't think that is the
We will
scenario.
let her proceed.
Yeah, let's keep the discussion.
Share one process where the standard model contribution is very small.
That's a good strategy.
You can look in places where it is big.
Yeah, yes. We should look at a lot.
Everywhere, right?
Yes.
Small, big,
No, no,
everywhere.
that's not good.
Alright, if you find an effect there,
Okay,
The
so
effect of these operators is just not changing the rates, they can also change the angular observables significantly, so there it might be important, so there are.
If I recall, all these process, processes are known up to third order interpretation, QC.
Yeah.
And then, so you have corrections, let's say up to 5% level. On top of that, you look at
Yes.
what are the corrections, because 5% is, if it is big compared to the precision of the experiment, then these things are important. So you have to add these parts. That is the spirit that these things are.
no, it doesn't have to be like that. In certain things like top operators, we don't constrain it to 5% amount, right? I mean, new physics can alter those operators in a big way. Right, I mean, there are certain operators where our constraint is very.
Variable or not.
Tau operators can be order one, you can see the
Given the large number of the dimensionality, the number of parameters, I think this is a very difficult question. If not, it will becoming redundant. You can always fit in something.
No, it doesn't have to be hidden in the NNO connection.
No, it's not actually. I'm saying.
Can be
I'm
order one.
not saying that. What I'm saying is actually, for example, this process in QCD, let's say that is the dominant correction which can come from standard model. You know, let's say 5% accuracy. And the experimental, observed, results are more precise than 5% level. Then you need to include such corrections.
No, no,
It can
Why,
go-
why not? I can go to next one.
No, let's not. If you go to large enough invariant, you can see a big change from, it doesn't have to be a 5% effect. As you go to large invariant mass, as you approach the scale lambda. If lambda is only 1 TB or something, if you go to large lambda at LHC, you can see a big change in the complex. It doesn't have to be a few percent and all that. At 5 invariant mass, you can see a big change. If there is difference. If it is a standard model, then what you say is right. Then it has to be a small correction being consistent with NNO correction and all that. But if I'm actually introducing another higher dimensional operator with one more lambda, as I approach lambda, I start seeing a dramatic change in the complex.
Absolutely, so we'll go as much precision later procedure, please.
So,
But one question, from your diagram, it looks like, at least naively, even the vector boson masses will get corrected by this third dimension now. See, if we have a VVH vertex,
yes,
so they should correct the,
yes, we have
and
taken,
both, they are measured very, very precise.
So that actually constrains the operator coefficients, the mass is a measured
It's
quantity.
good that they are very, very precise.
The mass is a measured quantity that constrains many of these coefficients from the solution, because the mass is a measured quantity. So when we redefine and write the mass in terms of these effective operator coefficients, that constrains the effective operator coefficients. The mass is known, so we have measured the mass of the
we
set
have
boson
taken.
for the W boson.
Yeah, whatever.
Yeah,
I
so
mean, you can use it to constrain your,
exactly, so we use that to constrain some of the operator coefficients.
yeah, so
So the mass
what
is one
is the result
observable.
of that?
The mass is one observable, so like, So they actually constrain some of these observables. So some of the Wilson coefficients.
No, but when you say constraint, I mean, that's a vague term.
It's not big, it's basically a direction. It's a direction. So it's like.
So if you only look at, for example, the W boson mass
Yeah,
and the width.
yeah.
Now, what can you say about the dimension 6 operator? Not all of them, only
Yeah, some of them
few
will
of
be
them.
Yeah, so few of them will contribute. So say it will be some AC1 plus BC2, which would modify this combination of operators, which would modify the W mass. So we write down MW prime squared is equal to MW squared term times this operator coefficient. So we know that we have measured this MW prime squared. So from there, we basically know so we know what, so we know MW in terms of the standard model parameters. So from there, we are able to constrain
Yeah,
this,
extend the method, I want to know,
the values.
yeah.
So I don't have those at hand. So
So-
like those are done. Yeah.
So there are, if you make sure that you respect custodial symmetry and so on, you can make sure that modifications, uncontrolled modifications, the low parameter and all that are very much under control. So you will not get any constraint on W mass.
Yeah, so W
mass.
exactly.
If you go in certain directions of the operation. But if it is uncontrolled, if it breaks T or custodial symmetry, then you can get a very tight.
Yeah, so I have shown here the geometric mean of the PTs of the two jets and the number of events. This blue curve is the standard model curve, and overall, what we find that the effect of these higher dimensional operators are amplified at the tails of the distribution. So these are the VBF specific cuts that we have utilized to separate the higher dimensional operator effects. So whenever we include the effect of these higher dimensional operators into process into a particular interaction, what we find that the rate of as I define the set of cuts here for the BBF process. So I have shown here the efficiency of those cuts as a function of this C over lambda square. So the efficiency, this y-axis is defined as the ratio of the rate of the process, which is a function of the Wilson coefficients after the cuts to the rate of the process before the cuts. So here I have focused on three particular operator coefficients. These are all of them are fermionic interactions that induce this gauge-gauge vertex modification and this gauge-gauge Higgs quad gauge modification to quad Higgs gauge modification. So these this kind of process, this 4-point process, this is a VBF-like process, but you see here we have one propagator less than the standard model VBF process. So the rate of this process is enhanced compared to these other processes. So this kind of 4-point interaction of quad Higgs gauge vertex is coming from these two kinds of operators, and within it I will focus on these two operators carrying this vector current that have the same helicity as the standard model, which is a left-handed current. If we have it is a W propagator here. So you see that these current operators carrying vector current, they will interfere with the standard model. Whereas this dipole operator that has a chirality flipping interaction, that will not interfere with the standard model, because in the standard model we have the fermions are of the same helicities. So there is a distinction here between the operator that interferes with the standard model and the one that doesn't interfere with the standard model. So we can tell for the dipole operator that does not interfere with the standard model, which is a chirality flipping interaction, you see that the curve, the efficiency of the cuts is symmetric around this C over lambda square. Whereas for the operators that interfere with the standard model, we can see that one of them interferes constructively and the other one interferes destructively here. For positive value of C over lambda square, the rate is falling. So Oh, it's the standard model efficiency when the Wilson, this is the efficiency when I have only the standard model terms. That's
Sorry, what does efficiency mean? It is,
It's
of fraction of
selection criteria.
by the VBM.
Yes, yes,
So you're saying that if, C or lambda is large,
yes.
then a smaller fraction of events are kept by the standard VBM cuts. Is that what this is?
Because that the one firstly we shouldn't go to such large values of C over lambda square as
Why is it? Why is that happening? As you go to large C over lambda, why is the efficiency dropping? For the green curve, why is that
Yes.
dropping? The green curve you
Yes.
said is a dipole operator, that
Yes,
it
yes,
doesn't have a
yes.
standard model part.
yes.
You're saying the standard VBM cut will kill most of the events.
Right.
Why is that? Because they are no
Because
longer a forward or something?
Because I am applying cuts that is that are standard model like
For standard.
standard model bridge.
And so it is not picking up. But they can be retuned, I guess, and then you can pick up.
I need to be
Yeah.
close to the standard model.
But you are not able to find out which in the standard cuts is what.
Yes.
Filling.
Yes. Yes. So here I will show in the kinematical distributions of the jets. So here it's I'm showing here the rapidity gap between the two jets. The correlation between the rapidity gap of two jets against this geometric mean of the PTs of the two jets. So for the standard model, this one is as you see that the geometric mean is the average geometric mean is around 200 GeV, 100 to 200 GeV, whereas when we have these higher dimensional operators, for these these plots I've chosen it to be 0.1 Wilson good, 0.1 TeV to the minus.
The colors or the cross sections?
Yes, this red color indicates more number of events. So the most of the events are in case of the new physics are populated with around 200. I mean, here we can see that the PTs of the jets are reaching above 500 GeV, and the rapidity gap is yeah. Yes, between the two jets, it's around 4 here, whereas in the standard model we still have higher rapidity gap.
So the top
5.
most is standard model
Yes.
and the lower two is.
Are higher
values
dimensional
of C's or different
Yes.
operators or.
different values of the Wilson coefficients, different kinds of Wilson coefficient. This one is interfering with the standard model, and this one doesn't interfere with the standard model. So the one that doesn't interfere with the standard model, as you see, that for a very small rapidity gap between 3 and 4, the most of the events are lying within this rapidity gap, whereas for standard model it's about 5. So that's why those cuts are very sensitive.
By the way, why did you choose the 2-photon channel? Why not something else like
Yes,
that?
we want to teach. That's what it
There's no particular reason why.
No, you can
But you have done the study only including.
of the jets. Yeah.
So the branching rate is small, right?
Yes, but it's a clean channel.
Yeah.
So here is the signal significance for different values of Wilson coefficients, bin-wise for the geometric mean of the PTs of the two jets. For the operator that doesn't interfere, we see that the significance increases with along the bins of the PTs of the jets.
This is
So,
for what?
that doesn't
Sorry,
Yeah. 0.3 TeV to the minus 2, and this third column doesn't interfere with the standard model, and these two interfere with the standard model. So the one that doesn't interfere with the standard model, as you see here in this operator, so this is a field strength tensor that has a momentum dependence here, del mu w. So so in the total rate of the process, the total rate will grow as E squared over lambda.
So for C equal to 1, this will be some 1 to 2 TeV, something like that, right? The lambda will be 1 or
Yes.
something in that range.
Yes.
Is where you get,
Yes.
that's the bound or that's
Yes, we are.
The
These
bound
are
operator.
just some illustrative values of.
Is that the boundless operator, the last one?
No. This is the statistical significance of the events in the different PTs of the jet.
So I can turn it into a bound, right? If I look
Yes,
for some
yes,
95% confidence
yes.
level exclusion or something. And that you have not, you don't show that, I guess.
Yes.
You're not showing. Okay.
So the next process is this Higgs plus photon production at the LHC. Now the Higgs plus photon has not yet been observed at the LHC. And this process in the standard model, as I was telling that to consider processes that are very sensitive to new physics effects. So in the standard model, this Higgs plus photon production, we see that at the tree level it's basically quarks in the quarks in the initial state, and this coupling with the quark Higgs, it's Yukawa suppressed. So even if we consider the heavy quarks, bottom or charm, it's a Yukawa suppressed process. It's that has very small cross section, and these tree level interactions are also having very small rate in the standard model for Higgs plus photon production from PP collisions. So if we have these operators, these dipole operators and these bosonic operators, the dipole operators induce this direct 4-point quad Higgs gamma vertex, and this bosonic operators, they induce this photon Z, and suppose photon H vertex or Z photon Higgs vertex. So these kind of operators, they can lead to the production of Higgs plus photon from proton-proton collisions. So what we find that in the standard model, the rate is extremely small for this Higgs plus photon production. But if we include these higher dimensional operators, the rate gets enhanced. So if we find any enhancement, if we are able to see Higgs plus photon production any day at the LHC, so that will essentially indicate the presence of these operators. We have decayed the Higgs to 2 bottom and considered very boosted kinematic regime where I'm not able to distinguish between the 2 bottom jets decaying from the Higgs as 2.4 radius resolved jets, but I have considered here as a 0.8 radius fat jet. I have considered here very, like I said that I have considered boosted kinematics. Like I have shown here the cuts, which is the jet of the PT should be above 200 GeV. It's a 0.8 radius fat jet, and the photon is also required to be at least 250 GeV PT. So these are extremely high cuts because the background for these processes is also very large. So as I have considered here Higgs to 2 bottom, and the 2 bottoms are not going, I will see it as a fat jet. So jets plus photon is a huge background in this process. And the other processes are also contributing to the background, like top gamma plus jets. Standard model rate is extremely small, but this jets plus photon background is very large. That's why I need to go to high energy. So, so the CMS has carried out this analysis of the search for a resonant particle decaying into Higgs and a photon. So, where the Higgs is decaying to 2 bottom. So we recast that measurement and we reinterpret that measurement to put bounds on these Wilson coefficients from the uncertainties of these Wilson coefficient from these uncertainties of these measurements in the invariant mass of the jet and photon. So these are the order bounds that we are getting when we consider one parameter at a time, and when all the parameters are considered together. So the
big question: are these bounds on these operators? So these also contribute to some other processes, right?
yes.
So are these of the same ballpark as the
The bosonic operators, as we see that they are loose here, so they are already constant from other processes. Yes. So in case of H gamma, their effect is not. I mean, they need to be larger in order to see their effect in H gamma.
These could be combined with those others.
Yes.
Elevated.
Yes. So the dipole operators, they can be constant to point of order Wilson coefficients. So
Sorry, the signal when you say M equals 850, what M is that?
sorry.
Oh, this is the CMS plus, right?
Yes.
What M do they mean? M is 8.
They have considered some UV models for their analysis, and they are trying to see whether that they have carried out this search for a resonant particle.
It's not the Higgs.
No.
They have done.
Yes. So we are using that measurement to see if I can put bounds in case of Higgs plus photon. So, and then we carry out this search at the HLHC2, and what we try to see the after getting the bounds on these operators at 13 dB LHC, we try to we find some benchmark points, and we see whether we are able to find any signatures for their effects at the HLHC. So again, this is the energy of the photon. So the signal is very hard compared to the standard model background, and moreover, the leading dominant background is this jets plus photon background, which, as we see, even if we consider the mass of the jet, this mass of the jet is peaking at a low value for the jets plus photon background, whereas for the other signals, as well as the standard model, we have a peak at around 125 G.
So what is the bound like? Previous transparency you showed that 13 dB bound.
Yes,
What is it like
yes.
previous transparency.
Yes, I will show it in this table.
Okay.
So then this was the cut-based analysis, and then we also try to optimize this search with the multivariate analysis using the boosted decision trees, considering different kinds of variables. Such as the photon, PT of the photon, the mass jet, the n subjettiness, number of subjects within the fat jet, and the scattering angle of the photon in this 2-to-2 process, and so on. So these are some variables that are functions of the energy dependent variables of the final state products. So what we find that with this multivariate analysis, and this was the cut-based analysis for different benchmark points. So, for example, if I look at these two benchmark BP1, BP2, they correspond to fermionic operator, and this one is the bosonic operator that induces this gamma Higgs gamma or Z gamma vertex, Z gamma Higgs vertex. So what we see that for the fermionic currents, these the required luminosity is around for 3 sigma signal significance is of the order of 1000 femtobarn inverse, and for the bosonic operators it's still large. Whereas if we include this multivariate analysis, we are able to get very high signal significance, as well as the required luminosity for 3 sigma significance is reducing. So the multivariate analysis, it optimizes the search channel.
What is the multivariate analysis? What kind of?
So here we consider the different kinds of kinematic variables all together.
Okay.
Or we apply all
Did you match to a differential distribution? You match to a differential distribution, or like you look at many variables together, all the kinematic variables together?
Yes.
But not match to a differential distribution.
No.
Okay.
So you can consider like it's a kind of hyperdimensional space of all these
And
variables
what's the
together.
LHC bound like for that operator?
Yes, so we are
You showed that in a like
yes.
slides back. What?
yeah.
Yeah, here, what is it like?
These are
Which all these operators contribute for X plus 1 for one.
Yes, yes, these are only
All
for,
of those operators.
yes.
And they're about point 0.42 inverse T squared.
Right.
Okay.
So we have roughly, so your overtime, so that we can take 5-7 minutes.
Okay,
But like
so I will,
Questions?
yeah, so I'll brush up quickly. So, whenever we need to, this is again one of the critical points that we need to take care whenever we do any EFT analysis, that we need to be in the valid regime of the EFT. So, as we are expanding this Lagrangian, here so I have written in terms of amplitude square, in terms of the higher dimensional operators. So, I am expanding this series. Throughout, I have considered up to dimension 6 square order, not only linear order. So I need to ensure that I am not making any error by truncating the series here, or at any higher order. Like whenever I'm truncating a series, I need to ensure that actually my series is converging. And the higher order terms that I'm not that I'm neglecting are really small. So, in case of operators that interfere with the standard model, it is generally seen that the interfering term with the standard model is dominant compared to the square order, this 1 over lambda to the power 4. Like suppose if I consider dimension 6 operator, it interferes with the standard model. So it will, in the total amplitude square, it will have 1 over lambda squared term that interferes with the standard model and 1 over lambda to the power 4 term, like d6 squared term. So that's, and this d6 squared term, which is of the order of 1 over lambda to the power 4, that can also arise from dimension 8 operator that interferes with the standard model. So we need to ensure that that we are not making any error by neglecting this term. So in cases where this interferes with the standard model, if this is the quadratic term is less than the interfering term, the EFT is valid. Like the higher order terms will be subleading ones. Even if it is greater than the interfering operator, we can still go to a regime as obtained by this ratios of the terms, corresponding terms. If you can, one can obtain this that if
I don't understand your case too.
Yeah.
Because that can happen when the dimension 6 operator is not bigger than the standard model. So generically it cannot happen because this is supposed to be all small corrections to the standard model. So is it because you have chosen some kinematic region
yes,
where the standard model effect is small?
Yes. That could be one case. Also, there are exceptions to this this criteria for cases where we do not have any interference with the standard model, like the Higgs plus photon, the dipole operator, the chiral flipping operator that does not interfere with the standard model. So, for those cases, we need to ensure that suppose I am carrying out my experiment at 14 TeV LHC. So roughly I can say that the lambda, 2 proton beams are having initial proton beams are having energies of 7 TeV. So each pattern I can say roughly carrying 1 to 2
But
TeV.
in the data that you analyze,
yes.
Are there things that correspond to case 2?
One cannot say with definiteness that it corresponds to case 2 or not. We need to see whether the interference with the standard model is larger or not. So if it is larger, then we can say that the quadratic term is smaller, which is generally the case when a standard model interference is there. So we are in this case. But if this term is greater, even if this term is greater, if I take the ratio of this term, it is something like this, C over lambda squared, E squared by G squared. So if there is a new physics dynamics where this G star, the new coupling, is greater than the standard model coupling, so this means this C can be larger. So that's a strongly coupled theory. So there can exist some theory like that. So for that, we need to ensure that we are in this particular energy regime. So if I'm assuming some value of C and I know my GSM, so I need to be in this energy regime given by this range. So here, as long as I'm in this regime, even if I'm the quadratic term is greater than the interfering term, I'm not making any error. Okay, so essentially the validity can be ensured by restricting to a particular. I mean, I need to assume some value of C, and that means I need to make some assumption of the UV dynamics. Okay, so I will very briefly discuss this non-resonance signals for axion-like particles. So as we know that they are pseudo bosons that appear in many standard model extensions from the breaking of a BSM symmetry. So they can be described by this LPFT can be described where these ALPs arise from the breaking of a BSM symmetry. And suppose there is a very heavy scale sitting at lambda, where the new sector is sitting at very heavy scale lambda, and that has been integrated out. But from the so there is some BSM symmetry, and when that BSM symmetry breaks down, it can produce some pseudo Wollstone bosons, which are lighter, than this heavy scale. So I described those light particles as ALPS and consider their effective field theory. So their masses are smaller, are very lighter, and it is a very good chance that since they being light, they are likely to be detected first as some source of BSM. So these are some effective operators. So I will discuss the interactions of ALPS with the heavy standard model-like particles, mainly in this work. So I have considered here the non-resonant production of ALPS through this gluon production, gluon fusion. And these ALPS are decaying into Higgs, non-resonantly. So decaying into Higgs, I'm seeing here the production of Higgs plus Z production, gamma Z production, WW production, and multi-boson production of WW gamma. So these are the four processes that I'm seeing, and in each of the four processes, the ALP is a non-resonant particle that is mediating these processes. So here, the cross section, each of these vertex of gluon ALP, or since it's a pseudo-Wollstone boson, the couplings are all derivative couplings. So from these operators, so each of these couplings are derivative couplings. So essentially, if I consider Higgs Z production, so since it's an S channel process, so there is 1 over S dependence. But since this coupling is a derivative there is a derivative coupling, so there is a momentum dependence here in this coupling. There is a momentum dependence here in this coupling. So overall, and these couplings are 1 over lambda, 1 over dimension 5 operators. So essentially, the total process will go as S times 1 over S times S by FA square. I'm considering FA to be the cutoff scale. So it's the total rate of the process grows as S over FA to the power 4, total rate. So, what we see that in case of the standard model, these S channel processes are generally they fall as 1 over S, but in case of the ALPS, although they are light particles, but we see an enhancement in the rate of the process along this energy variable. So here, to ensure that I am really in this non-resonant regime, how do I ensure this? This is the cross-section for the various processes against the mass of the L. And I'm seeing here that till 100 GeV of mass of the L, starting from 0.1 GeV, the cross-section is not changing at all because I'm in this non-resonant regime. So as long as I am in the regime where the invariant mass of these final state particles is the mass of the ALP is less than the invariant mass of these final state particles, I am in the non-resonant regime. So that is why I see that till 100 GeV, the cross section. I see no resonant effect. The resonant effect is appearing here. So I have carried out the analysis that is valid till about 100 GeV of mass of the ALP. So, and then I focus on the boosted regime for these final state particles. So, for example, this is Z gamma production from gluon fusion mediated by this ALP. So, I see the invariant mass of this Z gamma. Here I have not shown here, but all of these are energy dependent processes. But the thing is that for the signal, it is always enhanced compared to the standard model processes that mostly fall as 1 over S. So since they are derivative dependent interactions of the ALPs, so I am able to distinguish the ALP interaction from the standard model ones, although the ALP itself is very light. So I am able to get at this high energy regime and able to distinguish them. So with this non-resonant ALP production, I see that this hatched region for this coupling of ALP with the Z gamma against the mass of the ALP, that till 100 GeV, I am getting this bound of on this coupling of ALP Z gamma, which was not being probed by other experiments, such as, we can ALP Z gamma, we can probe it with Z going to gamma plus invisible searches. So there are a lot of mono-Z searches at the LHC. We can put constraints on the ALP with the ALP coupling with the Z gamma. So with the non-resonant regime, these are the hashed regions that I'm able to constrain, which are all of the constraints from other experiments, they assume some certain kind of model dependence, like about the theory. So, like here in my case, there is a caveat that I need to assume that there is a gluon-gluon ALP coupling existing. So, one could have done this process at the LHC with a vector boson scattering process that is initiated by quarks. So, vector boson scattering process, again, we can have some T-channel process where the ALP is mediated in the T-channel, and one can obtain some bounds, but those bounds are loose compared to the gluon fusion, as the rate of the process is enhanced.
It also depends on your C by number.
Yes. Here in these plots, I have chosen the gluon ALP coupling to be 1 TeV, the minus 1. I have just listed down different kinds of constraints. The assumptions and the characteristics for different processes of coming from the different processes at the LHC. So these are the different kinds of assumptions that we need to assume. And lastly,
Your way.
Okay. So
if you could just quickly tell in one sentence. Yeah, maybe you summarize. Yeah.
Okay, it's okay. So, yes, sorry. So the BBF, I have described some of the processes in the SMEFT here. For example, the BBF process that receives leading SMEFT corrections at dimension 6 using the kinematics of the tagging jets. And the other process is this Higgs plus photon production. And where we apply these jet substructure techniques, multivariate analysis, and all. And the other sector is this ALCH with an EFT approach at the LHC, and where the LHC is crucial to probe the heavy ALPS and the couplings to heavy standard model states. And the search was in non-resonant signals with this Higgs-Strahler-Diboson and Riboson productions, and the bounds are competitive, and they are independent for a large parameter space. They are independent of the values of the mass of the Earth and the decay width of the Earth. So a lot of different opportunities, even at future colliders also. So with Run 3 and HLLHC, we have lots to do and to enable discovery of new physics. By improving the analysis techniques, by looking for the unconventional signatures and increasing precision and assessing the value of the analysis.
One quick question. So what I wanted to ask earlier, and do that, see if the dimension of the space in which you are trying to fix a point, basically trying to fix all the couplings from observation is 2,500.
Yes.
Is it a practical goal to pursue? Do you want to? I mean, do you even have the right, do you even know the right machinery to address the question that where is my coupling? In the space of couplings, where do I sit? Yeah.
All of them don't contribute to the process, right?
No, but you have to have all the analysis done to show that I'm yes. That is in a 2,500 dimensional space.
Yes.
Yeah, so that is extremely difficult. So basically, like from every process that we do. So let's say, for example, we are studying some boson process. It is compartmentalized into different kinematic phase spaces. In some part of the kinematic space, some of these operators contribute and some don't. In some other parts, some of these operators contribute, some don't. So we know these a priori.
Right. And so it's a very specific exactly that would be designed.
Exactly.
So there is a pointed
very
question.
small spaces.
Yeah.
If it is a very pointed question, that's
So
what trying to
every-
solve, then that would help.
Yeah, so
Rather than having a general.
yeah, so every process actually is multiple observables. So like one single, say a W boson paired production, which will like different parts of the kinematic space will actually can be treated as a different data point. And in each of these, we'll have a constraint or a linear combination of some of these operators. So to break this degeneracy, we need to measure many things. So for example, say as an example, the Goldstone boson equivalent here, we know that at high energies, the WW process would kind of be like the G plus G minus. The WZ process will be like a G plus minus G zero production. Similarly, so from the Goldstone boson equivalence theorem, we'll be able to take 4-5 processes, and there are only 4-5 operators contributing in that set. So by measuring those 4-5 processes in that energy regime, we'll be able to completely decouple those parameters in that regime. But like this 2,500, it's difficult. So we have to like really
This
figure
game
out.
was played earlier for Susi also, right? So it's just the repeat of that, but with a different focus. You are looking for some contribute data point which actually shows 6 beyond standing model. But until then, that's all you can do. You cannot do.
So basically, your analysis is good only when the actions are sufficiently massive. But independent direct searches, how much is the parameter space is already ruled out?
Yes. So, for example, if I consider this mono Z search, this green region. So this green region is the mono Z search. So I am considering here that the action-like particle is it is a collider space. So at the collider, I will see it as a missing energy. So assuming that with that assumption, I am able to rule out this region. So with the non-resonant production, I am able to rule out more regions. Similarly, for mono W search, it is this region I am able to. So, I mean, for direct searches, we need to assume some value of mass of the and some value for the width of the. So that will again involve some modeling assumption.